Hello, it's Dr. Andy here. So here we are with a blank spreadsheet, and I'm going to give you a demonstration of chaos using the simplest possible equation and using the simplest possible setup, I think. So we're going to start off just simply generating everything from scratch here. I'm going to stick the number 4 in that box, and I'm going to stick the number 0.3 in this one. And over here I'm going to stick in a number just slightly bigger than 0.3. I don't know how many zeros I can get away with before Excel just, that survived, truncates it down to 0.3 again, but that seems to work. Okay, so the equation we're going to use right now is called the logistic equation, and it's the simplest example ever found so far of chaos. So the simplest equation that you could generate. So in order to do that, I'm just going to type this stuff, and you can type along with me if you want to create exactly the same thing. So I'm going to use this constant times the previous value in the sequence, which is going to be that, times 1 minus the previous value. And that's all that goes into the next cell. And because we're going to rely for all the columns, sorry, all the rows that we generate from here on this value 4, I'm just going to make that so it's no longer relative by sticking dollar signs in front of the A in front of the dollar. Okay, so really simple equation there. So let's copy that and just copy it down. And we're going to go for about 500 of them, I think. Obviously, this series will carry on forever, but if you have more than 500, it gets hard to graph it. There you go, that's about 500. And so now we've ended up with a sequence of numbers, where if we look at the first one, you see every new number is based on the previous one. And we're just taking the previous value, multiplying it by 4, that's what that number is, and multiplying it by 1 minus the previous value. And it's producing this interesting sequence of numbers. Now, if we highlight the entire sequence and then insert a graph, line graph, you can see this is what it looks like. This, ladies and gentlemen, is chaos. We've produced a chaotic time series with an incredibly simple equation. Well, sorry, a chaotic series. We can treat this as a time series because a time series is just simply, well, most time series are just simply a sequence of sampled data items, and so there is no difference, in fact, between a sequence of numbers and a sequence of sampled data items. So we're going to act as if this is also as if we've created a time series, with no loss of generality, as they say. Okay, so next step, I'm going to delete this. Next step is to do exactly the same thing. Copy that across to here. Now we've hit return. Now we've actually got this value is dependent on our slightly bigger than 0.3 value. Okay. And let's do exactly the same thing. Control C for that, and then copy it down until we've got the same kind of size. Oops, I've overrun. Come back. All right. The same amount, the same size. And now the same number of rows. So now I'm going to pick on this and this and graph them. And there you go. We've got two different series generated here. Now to stretch it out, you have to stretch this out in order to see the difference. And the two series begin by overlaying each other, and then they start to diverge. And they diverge more and more and more until basically you've got two entirely different series. But we generated these two series using exactly the same equation with the same scaling factor, but the difference between the two is just simply this, however many zeros that is, and 1. Some tiny, tiny number which has made these two series evolve entirely differently. If we scroll down the series, you can see here that we've got the 84th one, we've got something virtually 0, and the other series is 0.7. So, now to make this a little clearer, maybe the easiest thing to do is to turn this into a sort of more visually attractive series, a series that's easier to look at. So one of the ways of doing this is to say that this series we've generated is not, we're going to treat the series that we've generated as if it were the rate of change of another series. So we're going to, and I don't know whether you can see, but this series generated basically roams between 0 and 1, so it's actually balanced around, or symmetrical around 0.5. So we can type 0.5 minus this value. And here I'm going to type 0.5 minus this value plus this value. So I'm going to sum the differences. I can treat this as a positive and negative going waveform, and then I'm just going to sum it. And by doing this, I'll make the difference between the way that these two different waveforms have evolved clear. So again, if I take that and copy it all the way down here to 500 and whatever it was we got to, we end up with and I'm going to do that twice, in fact. So I'm going to just copy the whole thing over. There it is again. Copy it over. Control C, Control V. So we have two time series that begin to diverge, if you see that, again, the numbers. And this, scroll up the top, this time series is just simply this time series effectively summed. So now if we take these two, in fact actually I don't need to scroll down, I just have to click on there and there and generate a graph of those, what do we get? We get this graph. So here you can see pretty clearly how these two series have diverged. We've got a tiny fractional difference between the generating equations of these two series, and yet they're entirely different. Now there's lots of things I like that I think you can get out of this graph. One is this idea from chaos of sensitivity to initial conditions. So we've got an incredibly tiny difference between these two series, or the generators of these two series, and yet they've created very different graphs. Secondly, if I actually said to you that one of these was the dollar against the euro and the other was the dollar against the pound sterling or something or other, ignoring the scale, there's no reason why you wouldn't believe me, because these kind of shapes are really characteristic of the financial markets and a lot of other things. And this is what chaos looks like when you see it as a time series. I want that to think in. This is what chaos looks like when you see it as a time series. That's not proof that the financial markets are chaotic or other things that have time series a lot like this. Okay, that's not proof. We'll come to the proof later. There is a proof. It's difficult and it's complicated, and I'll have to explain it to you. But you can see already that there's an enormous visual similarity between any one of these two graphs, and obviously we can create loads and loads of different ones, and financial time series. Sensitivity to initial conditions you've seen, which is stunning. It should go without saying, but at some point later maybe I can produce a video looking at this. That if you had something that was a normal time series, like a sine wave or whatever, the fractional differences that we've seen would not create this massive change in the shape of the waveform. So most things in nature, the errors, prediction errors of most things in nature grow linearly. Chaotic systems, this is a corollary of sensitivity to initial conditions. Chaotic systems, the rate of error growth grows exponentially. So if we were to consider this series here, which is the first one we generated, as a real-world time series that we'd actually got from somewhere or other, rather than me having generated it. And let's say that we had the best modeling gear that you could buy in the world. So the best, I guess, machine learning system or something or other, or the best analytical tools to try to look at this time series and work out what the generating function was. And this is something that science does all the time. It looks at time series, and tries to work out what the generating function behind that series was. So let's imagine that we did that, and we got really, really close. And we actually generated a model that was almost identical to the generating model for this series. But we've seen here that the tiniest difference will throw your predictions completely out of kilter if there's chaos present. One other thing to look at, just looking at these equations, the two fundamental necessary requirements for chaos are present. We've got feedback in that this value is dependent on the previous value, do you see? So B2 is dependent on B1, that's feedback. And we've got nonlinearity. So B1 times 1 minus B1 gives you something like a square law kind of nonlinearity. So these are the sufficient conditions for generating a system that has feedback and nonlinearity is very often capable of chaos. Normally it's determined by the parameters, and this is why I kept this parameter separate, because if I put it down to something lower, suddenly no chaos. Absolute predictability. Again, no chaos. But suddenly when it gets up to 4, this in itself is a really interesting area of chaos theory. the process of bifurcation, which leads to the development of chaos. But 4 creates chaos. Isn't that fun? I think maybe we can stick in, you see what happens when we go above 4. Woo! So, actually things have got so out of hand here that the that the internal calculation engine of Excel has given up. Okay, so I hope I've illustrated some of the fundamental characteristics of chaos in this little video. Sensitivity to initial conditions, the inability for somebody to be able to model it, the fact that these time series generated look a lot like other time series that you'll see very frequently in finance and, dare I say it, climate. And this will be the beginning, the first stage in explaining why it is that climate is chaotic and what that means. Thank you very much. Bye.